thought we'd use this special TV program to draw together some of the themes that have been running through the course, particularly emphasizing the ideas that we developed in the first 10 units. The first of these themes was objects and how they interact with illumination. Now, you probably recognize these bits and pieces from your home kit. Here's an object, and it's being illuminated by our old friend, the laser. And if we put in this piece of card and bring down the lights, we see that we're getting a whole range of beams coming out. One beam going in, many beams coming out. In fact, this particular grating is a square wave one. But you'll know from the early units that we don't have to consider anything as complicated as that. For the behavior of any mask can be described in terms of the behavior of something simpler. In fact, in terms of the behavior of a cosinusoidal grating. So the situation which we have to consider is how a cosinusoidal grating interacts with a normally incident laser beam. Remember this animation? It shows the field on the output side of a cosinusoidal grating. Places where the curve is always zero coincide with totally opaque regions of the grating. This field can always be broken down into two components. A standing wave component, which reflects itself back and forth across the axis, and a component which has the property that it has the same value at all points in space. This is the so-called constant in space component. To see the practical significance of these components, we used a corrugated plastic model. At all points on the output side of the grating, the field is constant at a particular instant in time. As the normal plane wave progresses, the field on the output side of the grating bounces up and down. The other field component, the standing wave one, can be synthesized from two traveling waves of the same wavelength and speed, but which travel in opposite directions. In terms of our model, they arise from two sets of plane waves which leave the grating at an inclined angle. And here we see our three sets of waves coming out from our grating. Now, in doing this experiment, we of course have used a particular light source. So the next thing to remind ourselves and to consider is what would happen if we were to use a different light source. But before we do that, let's just summarize the actual experiment that we did here. What we did was we sent in one set of plane waves, and we got three sets coming out. And I'm using these rays to show the direction in which the plane waves come out. Well, now, the next thing we might do would be to change the wavelength. Instead of using red light, we might use blue light. And again, we would get three sets of plane waves coming out, but the angular spread would be smaller. Now, if we had both of those lights present, then of course we'd have 5 sets of plane waves coming out. And if we had a whole range of wavelengths present, why, we'd have a whole range of directions in which the plane waves are coming out. And under those circumstances, we would say that the illumination in our system was temporally incoherent. Well, that's one thing that we might do with the illumination. There's something else that we might do. Instead of changing the wavelength, we might keep the wavelength fixed, but change the direction of incidence. Now, when we did that, we would find that again we had 3 sets of plane waves coming out, but the direction was tilted round. And of course, if we had both of those directions present, well, we'd have half a dozen different beams coming out. And if you had a whole range of incident directions, why, we'd have a great spread in emerging beams. And under those conditions, we would say that the illumination was spatially incoherent. Now, you might think that this was something of an academic nicety. But in practice, these different types of illumination can arise in many practical situations. here's a set of plane waves. And they're being produced by a point in the front focal plane of this lens. The point has got a single frequency. So what's coming out here is temporally coherent. Well, something else that might happen is that instead of this point being on axis, it could be off axis. So once more, it's producing a set of plane waves, but they're coming off at a tilted angle. Well, even that is a little bit academic, because we don't just normally have nice little point sources like that. We obviously have got fairly extended sources, but never mind. Each point on the extended source can be thought of as being like a point source. And what this point and this point and this point is doing is, of course, producing its own set of plane waves. So what this broad source is producing is spatially incoherent illumination. And there's one other thing. I've assumed, by the way, that each of these points has got a constant frequency. It produces light of the same frequency. Well, pretty clearly, if I've got a whole range of frequencies there present, what would be coming out here would be both spatially and temporally incoherent. So to summarize this first theme that ran through the course, I could say that what comes out of an object depends not only on the nature of the object, but it also depends on the nature of the illumination.
The next theme that we'd like to remind you of is the way that we read out the information on the light beams leaving the object. And the simplest way of detecting this information is to put in a screen at a large distance. Now, since we're using a very simple illumination, a parallel laser beam, it's a very simple encoding. It's the Fourier transform encoding, and this tells us about the spatial frequencies present in the object. Now, there are situations in which it's this diffraction encoding we have to use to find out about the object. Do you remember this diffraction pattern, an X-ray diffraction pattern of hexamethylbenzene? It was shown in TV6, the program about the optical diffractometer at Cardiff. Or this X-ray diffraction pattern, this is a pattern formed by a man-made fiber. The thing about X-rays is that there are no lenses to form conventional images. Therefore, we have to rely on the diffraction pattern. And we showed you in the TV program how we compared X-ray diffraction patterns with optical diffraction patterns produced by models in order to deduce the structure. Now, another situation in which diffraction patterns are useful was shown in the case study on dislocations. This is the electron diffraction pattern of an aluminium specimen. And the regular arrangement of spots there tells us that the aluminium has a regular crystal structure. That's the information we couldn't find out by looking at a conventional electron micrograph. Now let's have a look at an optical diffraction pattern that you may well recognize from units 3 and 4. Or have a look at the other one, which was shown in the same place. Now, we told you in units 3 and 4 that these were diffraction patterns produced by the faces of 2 course team members. And I'll tell you now that one of them is Alan and the other one is Barry. But can you guess now whether this is Alan diffracted or whether this is Alan? I don't think I really ought to expect you to guess, since I couldn't guess myself when I was shown the pictures. But being told the answers, that in fact we've arranged them in the right way, this is Alan and this is Barry, I can hand-wavingly justify this pairing. The main difference between these 2 diffraction patterns is in the high-frequency region, the region away from the center. You can see that in the case of Barry, we have a fairly circularly symmetric diffraction pattern. And I would say that, well, Barry has beautiful curls. They're going to diffract fairly similarly in all directions. And so the diffraction pattern at high frequencies produced by fine structure like hair will be circularly symmetric. But have a look at Alan. His hair isn't curly at all. It's rather straight, well-groomed, one might say. And in this direction particularly, there's a fairly well-defined hair structure that I can see. Now, the structure in that direction is going to diffract preferentially this way, and maybe that's what's responsible for this clear asymmetry in this direction in the diffraction pattern. Now, I agree that's not terribly satisfying, and certainly if you were faced with a picture like this, you wouldn't be able to tell whether Barry was smiling or frowning. You couldn't even tell whether he was standing on his head. We really want to get from a diffraction encoding like this back to an image of Barry that we could all recognize. Now, that's where lenses come into the story. We want to change the diffraction field to produce an image field. Now, in order to do that, it's the first step one really wants to take is to bring the diffraction field a bit closer into the object. And one can do that very straightforwardly by inserting a lens. Since the lens is a distance f from the object, in the back focal plane, we will get a diffraction pattern, a pattern that's exactly similar to the pattern we saw earlier on the far field. Now, if I don't interrupt the light at this point, but let it propagate further on, then I can process it, if you like, with a second lens. And by arranging this lens so that it's a distance f from the diffraction plane, I'll end up with an image in the back focal plane of the lens. Now, let me just quickly summarize what this optical system is doing. The object here is in the front focal plane of the first lens. So the lens produces a transform in its back focal plane. This transform plane is in the front focal plane of the next lens. So this second lens will form an image on the screen a distance f behind it. What we're doing is taking a Fourier transform and then Fourier transforming that Fourier transform, and that gets us to an image of the object. Now, unfortunately, it's not a perfect image. Lens systems aren't perfect. A point in the object won't be perfectly reproduced as a point in the image. It'll be blurred out somewhat. Another way of looking at this is to say that each spatial frequency in the object isn't reproduced exactly the same in the image. There'll be changes of amplitude and there'll be changes of phase. Now, one effect of this frequency distortion is caused by the finite aperture of the lens. The high frequencies in our object are going to be diffracted a large amount. They're going to miss the aperture of the lens altogether, and so they obviously can't get through to the image. There'll be a blurring due to this loss of high-frequency information. Now, the fact that we can characterize imaging systems such as these lenses by a spatial frequency response is one of the main reasons for using the Fourier approach in this course. Another reason is the subject of spatial filtering. In this plane here, we have the Fourier transform encoding. Each spatial frequency appears at a different point in this plane. Now that means that we can filter or treat each point differently. We can block out some spatial frequencies, we can change their phases, and we can do this in such a way that we produce some desired effect in the image plane. Now, you all should be experts on spatial filtering, having done the series of experiments in Units 7 and 8. But let me just remind you of a couple of applications of spatial filtering that we've showed you in earlier TV programs. You may remember this example, which started off the program on optical microscopy.
These cells were taken from inside someone's mouth. We're viewing them through a microscope set for phase contrast. With the microscope set for ordinary bright field illumination, very little is visible. Set for dark field illumination, the cells again become clearer.
In that brief snippet, the bright field situation was the situation in which we didn't do any spatial filtering. There was nothing in this transform plane. For dark field imaging, we block out the zero frequency component. And the effect that has is to convert the phase information about that object, those cells, into intensity information. For the phase contrast system, instead of using an amplitude filter, we use a phase filter. And what this does is to change the phase of the zero frequency component, and again, it converts the phase information into intensity information. Now, spatial filtering was also the crux of the case study on imaging dislocations. In that case study, we were imaging a specimen something like this, a piece of aluminium. In the standard electron micrograph mode, we get a singularly unhelpful picture there's no evidence of dislocations, even though they're much larger than the resolution of the microscope. In the diffraction pattern, the crystal structure produces the array of points. And if we use an aperture to select the information distributed over one spot, then the coarse structure, dislocations and bend contours can be seen. So we've showed you how we get an image of the object that we can easily interpret. And we've also showed you how by spatial filtering in the transform plane, we can modify that image in some suitable way. We can even make the invisible object visible.
Well, so far so good, but we have been we've cheated a little bit up to now because we've dealt with only two-dimensional images, images in single planes. Really, we want to think about what happens with three-dimensional images, images which have depth as well as this sort of direction involved. Well, what would happen with that in an imaging system? Simple, a plane here would come into focus here, and a plane here would come into focus here. The trouble with that is that if we want to record it so that we can see it at some later date or show it to somebody else, we have to put something here to detect the field, say a photographic plate. But we can only detect one plane at once. Either the front of the image will be in focus or the back of the image will be in focus. And in fact, I've taken some photographs which show precisely that. Here, this telephone, the front is nice and clearly in focus, but the head shell is very blurred. So to get the head shell in focus, I had to take a second photograph. Now the head shell's beautifully in focus, but the numbers are all blurred. Well, those of you who know something about photography would say, well, so what? I could have made the aperture very small and got a large depth of focus on the photograph itself. Well, true, but what I couldn't have done is I couldn't have seen whether there was any writing down the side of the telephone. In order to see whether that was the case or not, I had to take yet a third photograph. Now, as it happened, there is nothing down the side of the telephone. But you didn't know that until I showed you this photograph. Now, that's a bit of a nuisance. What we've got in essence are three photographs just to show different aspects of the image. What we would really like is to be able to put all that information onto one plate. And of course, that's exactly what we do with a hologram. We get different angles, and what's more, we can get different focus planes. Now, in the TV program on holograms, we showed you that really did work. Here, the front of the telephone is clearly in focus, whereas the back is very blurred. If we focus the TV camera on the back, then the back is in focus, but the front is out of focus. Come back again, the front comes into focus, the back goes out of focus. Well, it works, obviously, but I haven't said anything about how it works yet. In that same TV program, we tried to convince you of the way in which it worked. We said that, in essence, what you've got to do is record the amplitude and the phase in the optical field. Not an image, the field. And how do you record amplitude and phase with detectors which can only respond to intensity? Well, somehow you have to convert the information into intensity information. What you do is you add in a reference beam, something with which you can compare the phase, if you like, of the field. Now, in the TV program, we took a very simple object, a non-object, a plane wave, and we tried to see what happened as a plane wave interfered with a reference beam. As the two beams converge, we look at the area of overlap with a microscope. And looking through a TV camera, the field is displayed on a monitor. And what we get are sinusoidal fringes. If we were to take a photograph of that, we would have a sinusoidal amplitude grating. But that's not really what we're after. That was a non-object. What we really want to do is see what happens when we put a real object in there. And we did put a real object in. We put a glass bottle stopper in. Now, with this bottle stop in place, the field is deviated, and the result is that the fringes are now modulated. Those nice clean sinusoidal fringes have become more complicated. Now, what effect does that have on the playback? Well, with the nice clean sinusoidal fringes, we get the standard 3 beams out. As soon as we modulate those fringes, well, it's still basically sinusoidal. We still get 3 beams, but they're not quite as simple as they were. We still have the straight through beam, and we still have a beam upwards, and we still have a beam downwards. But the beam upwards is diverging, as if from a virtual image back here. And the beam downwards is converging, as if to a real image down here. The fact that we've got 2 images is, if you like, the price we pay for going through this, adding in the reference beam thing. And all we needed to be able to produce this holographic recording was coherent light. But not just coherent light, any coherent radiation would do. In fact, in one of the case study TV programs, we showed you how we could generate a hologram with coherent ultrasound. This acoustic transducer is scanning backwards and forwards over a simple block of brass, and the holographic fringe pattern is being plotted out line by line on this chart recorder. The finished hologram looks like this, but of course we don't play the hologram back with acoustic waves. We can't see acoustic waves. Instead, we play it back with a laser beam. The advantage is that we can now see detail, such as the horizontal drill hole on the left of the picture, for instance, which, because it was inside the brass block, couldn't have been seen directly with ordinary optical techniques.
So the sometimes perhaps rather esoteric ideas of Fourier optics can very often find practical down-to-earth applications. But the real beauty of these ideas is that, irrespective of the nature of the image, the information content is the same.